and we're talking about extreme values. And the first kind of extreme value is called an absolute extreme. Sometimes it's called a global extreme. And so a function f of x has an absolute max, an absolute maximum at x equals a when f of a is bigger than or equal to f of x for all x's. Function f of x has an absolute max at x equals a when f of a is bigger than or equal to f of x for all x's. So what that means is that this y value is larger than, or it could be equal to, all the other y values. So it's the highest point out of all the points. This y value at a is bigger than all the other y values. So that's called the absolute max. And then I could change this word to minimum, and then I would just have to change this to a less than or equal to sign. So a function f has an absolute minimum when it's less than or equal to. So I probably, if I was being very precise, I would write this whole thing down again, and I would just replace the word maximum with minimum, and I would replace the greater than sign with the less than sign. But it's the same idea, so we'll just save some ink and not write all that down. So really what's going on is this y value at a is less than or equal to all the other y values. So it's the lowest point. It's called an absolute min, or a global min. Okay, so it's very important to know that endpoints can be absolute extrema. Endpoints can be absolute extrema. So what I mean by that is if you have a graph, that is the absolute max. It's on the end. So endpoints can be absolute maxes and absolute min. The word extrema is just the plural of extreme. So it means could be a max or a min. It's the Latin plural and still has survived in the math community. So. Okay, so those are absolute max and absolute mins. But now we're also going to have local extreme values. So local extrema. And a local maximum occurs at x equals a if f of a is greater than or equal to f of x for every x near a. The local maximum occurs at x equals a if f of a is greater than or equal to f of x for every x near a. So what that means is that this y value is bigger than the y values, but not bigger than all the y values. It's just bigger than the y values that are close by. So just in a small area close to it, it's the lowest or the highest one. So there could be far away a higher point, but it's the highest one near there. So it's kind of like if you're the fastest runner in Lebanon, you're the local champion, you're the local max. I guess in this case min, because you'd be less time than everybody. And then you go to a larger meet that's involving 7 cities, and you're not the absolute best. You're just locally the best. Okay, and then you can replace this word maximum with minimum. And change it to less than. And then there can be something called a local minimum. So I'm just trying to save us time in ink. There's an exact definition like this with the word minimum in place of maximum and a less than or equal to sign then. So same thing. Okay, then I also want to make sure you know that endpoints cannot be local extrema. Endpoints cannot be local extreme. So over here, that point is not a local max because it's an endpoint. It's just absolute. All right, so let's look at an example that has a graph that has a bunch of these types of extrema in them. So for this graph, I would like a point at -1, 1. And a point at -0.5, 2. And then at 0, -2. So it's going to connect like this. So -1, 1, -0.5, 2, and 0, -2. And then it's going to wander up to 2, 5, but there's going to be an open circle at 2, 5. And then it's going to go down to 1, 2, 3, 2. Then up to 4, 3. And then over from there. So that's 4, 3. This is 3, 2. This is 2, 5. 0, -2. 0.5, 2, and -1, 1. And the directions are state the extreme values and where they occur. Okay, so just give me one extreme value and where it occurs. Could be local or absolute, doesn't matter. Yeah. Okay, there's an absolute minimum at 0, and the minimum number is -2. Good. So, absolute minimum at x equals 0. So where it occurs is 0. We always talk about the x value being where it occurs. And then the value is the y value at that location. So the absolute minimum is at x equals 0, and the value is -2. Is there a local minimum there? Is that point lower than all the points near it? Yeah. So it's also a local minimum. If you're the overall champion, you're also the local champion, right? So this is a local min as well. So local min at x equals 0, and the value is -2. So that's important to point out that there could be both a local and an absolute at a location. That happens at 0. All right, what else? Yeah, Kristen. Good. Except there's not a point there. See how there's an open circle there? At 2? So there's no point there at all. So there can't be an absolute max there. Okay, so then you'll come back and you say, okay, how about right here? Is that the highest point? And I'll say, no, that's higher. And then you'll say, well, that's not the highest one either because that one's higher. Et cetera, et cetera. We could argue back and forth forever, right? So there's no absolute max. This graph doesn't have a highest point. Because if I pick a point that I think is the highest, there's always one next to it that's higher. So there is no absolute max. So that's important to point out that there may not be an absolute max or an absolute min. And on this graph, there's no absolute max. There is an absolute min. There's no absolute max. Good. Yeah. But what I'm saying is, if you say it's at 1.9, I'll say, well, 1.99 is higher. And then you'll say, okay, it's 1.99. And I'll say, no, 1.999 is higher. So we argue back and forth forever. And we'd never find a highest point. So that's why there's no absolute max. Good. All right, what else? What else is going on in this graph? Yeah?
Oh, there's a local maximum.
Yes, local max right here at x equals -½ because it's the highest point for all the ones near it. So there is a local max at x equals ½ because that point is higher than all the ones near it. It's not overall the highest point, but at least for the ones near it, it's the highest point. And the value is 2. Yes? Yeah, I did mess that up. Obviously, this is -½ Thank you, Colin. Appreciate it. So then this one would be -½ Good. Yes? Okay, good. This is a local min because it's lower than all the points near it. So local min at x equals 3, value is 2. How about this one? Is this a local min? It's lower than all the points near it, right? It is, kind of, but the problem is you don't know what's going on over here. Nothing's going on over there, and we've said endpoints can't be local. So if you look at it, it does look lower than the points near it, but we exclude endpoints for locals. Okay, what else? Anything? There is a local max here, because that point is bigger than or equal to all the points near it. So notice that there's a line under here, so it's allowed to be equal to the points near it as well. Okay. So local max at x equals 4, value is 3. Yes?
What about like first the values to the right?
So is everybody okay with this? Kind of strange. Everybody's okay with this? Okay, so now Michael's saying, what about at 6? That's a local max because it's greater than or equal to all the points near it. It's also a local min because it's less than or equal to all the points near it. So local max and min at 6, and at 7, and at 6.5, but I think you get the point if we just write down 6. The same thing happens at 5. Same thing happens at 5.5, but I don't want to write down all infinitely many points there. So local min and local max at x equals 6. So that for these last two, the point is there can be a tie. If there's a tie, then it's still called a local max or an absolute max. There could be a tie for absolutes as well, but that doesn't happen on this graph. Okay, I think that's it. Did I miss anything? Okay, let's look at one more graph. So this would be example 2. This one's going to be a lot simpler than the other one. So this is 1, 0, and then there's a hole at 3, 2. So the thing that bothers people about this one is there's an absolute min at 1. And the value is 0. But then there's nothing else. There's no absolute max. We already talked about that over there. And why aren't there any locals? Because endpoints can't be locals, and there's nothing else going on there, so. I showed this one because on a couple of the homework problems, there's only one answer, and people are worried about that. Because my example 1 had a lot of answers. And so it's okay if there are a lot of answers. It's also okay if there's not much of an answer. So don't worry about that as you're doing them. Just write down all the extremes. Okay, the next concept is called a critical value. And a critical value is an x value where f prime of x equals 0 or f prime of x is undefined. So it's just a definition. If the question asks for critical values, you just take the derivative, and then you find out where the derivative is 0, and you also find out where the derivative is undefined. Okay, now this sounds like what we did yesterday, right? Except yesterday we did the original function equal to 0 and undefined, because we wanted to know when the original function switched from positive to negative. And the possible switching places for it are when it equals 0 and where it's undefined. So this isn't a coincidence. It's connected to what we did yesterday. Okay, so critical values are critical for 2 reasons. So they're important for 2 reasons. And they're called critical values because they're important. So I wasn't joking when I said that critical values are critical for 2 reasons. That's where the name comes from. They're important. Okay, so the first reason they're important is what I just alluded to. It's a possible place where f prime might switch from positive to negative. Because f prime could switch from positive to negative if it crosses 0 or if it jumps over 0. So these are places where f prime might switch from positive to negative, or vice versa. And then the second reason they're important is these are places where local and, well, where any extrema could occur. Okay, so these are places where extreme values might occur. So if you're looking for extreme values, critical values are places to look. For example, over here, the slope is 0. So f prime would be 0 there. And we had a local min and an absolute min there, right? And also here, the slope is 0, and we had a local max there. Here, the slope is undefined. and we had a local min there. So it's a good place to look for where the extreme values might happen, where the slope is 0 or where the slope is undefined. Now, I'm not saying that every extreme value that'll happen, because this is an absolute min, but f prime is not 0 there, and f prime is not undefined there. So that's why I'm saying it's a good place to look. But I'm not saying that you find all of them if you look at those. But that's why they're important, because we can find extreme values there. So here, let me show you another graph. So what's going on at x equals 2? I guess I should be more specific. What's happening to the slope at 2? I'm trying to draw it flat there. So the slope is 0 at 2. So that means x equals 2 is a critical value. Since f prime of 2 is 0. So by definition, since f prime is 0 there, it's a critical value. Is there a local min or max there? No, there's not, because this point is higher than these points, but it's lower than these. It's higher than these, and it's lower than the ones to the right. So there's not a local extrema there. So I'm just trying to emphasize that these are places where extreme values might occur. I'm not saying there have to be extreme values at these locations. I'm saying they might occur there. Is this a critical value? Yeah, because the slope is 0 there, right? Is there a extreme value there? Yeah, it's a local max, and it's actually an absolute max as well. So there's also a critical value at 5. Since f prime is 0. And this time there is an extreme value there, an absolute max and a local max. Okay, so critical values are important because there might be local mins and maxes there. The graph I erased here had a bunch of local mins and maxes at critical values. But this is just further driving home the point that maybe there will be a extreme value there, but maybe, sorry, maybe there will, but maybe there won't. All right. So there's one more problem, but really not enough time to say that. There's something I want to say. So I do want to say this. Tonight's homework is calculator active. So what I mean by that is if it says find the local extreme values, you can graph it in your calculator and just look and see what it is, like we did with the graph at the start of class. I gave you the graph. We didn't pop it into the calculator to get it, but so eventually, over the next few days, we're going to find all these values without a calculator. And we're starting to figure out how right here. But for tonight, it's calculator active, so you're allowed to look at the graph to see what's going on. All right. Thanks for listening.